Hello, my name is Kanthi Sarpatwar. I'll be talking about FHE-friendly distillation of decision tree ensembles for efficient encrypted inference. This is joint work with some of my colleagues and some of my ex-colleagues. So our motivation comes from a typical machine learning as a service scenario. In such a setting, you have pre-trained models hosted on cloud environments and these capabilities are exposed to external clients in the form of REST APIs, for example. Our goal in this talk is to preserve privacy of the client data. So the people who use this service, you would like to protect the privacy of those clients, right? And we would like to keep the model intact. We don't want to give away the model. So we do this by using fully homomorphic encryption based privacy preserving inference. For a quick example for this is a typical hospital setting where you have a major hospital, for example, owning patient data and can build models on top of the patient data to predict, say, diseases such as cardiac arrest, diabetes, or cancer, some such disease. And they would like to expose these capabilities for clients who could be either individual patients or smaller clinics which do not have enough data to train their own models. Now, obviously, patient data in such a setting is highly confidential, so you would like some guarantees on the privacy of these data sets. Another example could be from a financial sector where you have a credit firm which owns, which has access to customer credit information, which is obviously private, and which can train models to predict risk, credit fraud risk, and again would like to protect the data privacy of external clients, right, for proprietary reasons. Okay, so as you may know, fully homomorphic encryption is a special type of encryption that allows you to perform computations on encrypted data without the need for a decryption key. So what is the problem? Well, fully homomorphic encryption is great with with evaluating low degree polynomials, but when it comes to sort of very deep circuits such as nonlinear, non-polynomial functions, it becomes really inefficient or close to impossible in evaluating these functions exactly. And machine learning is obviously full of these kinds of functions. You have, for example, sigmoid, ReLU, and any reasonable activation function is highly nonlinear. So this makes applying fully homomorphic encryption techniques directly to machine learning in a straightforward way. So what we propose here in this work is to take a pre-trained unconstrained model where particularly we look at ensemble of decision trees, which is a which can be highly complex with several hundreds of individual decision trees, and these and convert these models or approximate this model using another FHE-friendly model and use that FHE-friendly model as a proxy for this pre-trained model. And we do this with very little original data set. So our proposed approach is summarized in this slide. We start with, firstly, we have the original training data set, which which was used to train a pre-trained model, or what we call pre-trained model. It's basically a decision tree ensemble model. And so the assumption for this paper is that we do not keep the data intact for a variety of reasons. Instead, what we do is we take some statistics from the data, right? some training data distribution information, and we use that distributional information to generate, say, synthetic transfer data sets. And essentially the idea is to use that synthetic data set and the pre-trained model and use a knowledge distillation kind of a approach along with a certain architectural search to find a reasonable FHE-friendly model that will approximate your pre-trained model very well, very closely. Now, at the time, so this is the pre-training time or at the training period. Now, once this is done, you have a client who has test data or wishes or query data and wishes to perform a homomorphic inference. The client would sort of encrypt their query data and send it along to the cloud environment where this FHE-friendly model is deployed. And using the encrypted data and a public key, the model will perform FHE based inference on top of it, and then the resulting results will be sent back to the client where they can be decrypted. Okay. So the key thing to note here is there is no private key shared from the client to the service provider or the cloud environment. So this slide shows you a high level approach of what we propose to do for a single decision tree. You can naturally extend this to an ensemble of decision trees or any complex model. Essentially, you're given a model, which in this case is a trained decision tree DT on a given data set, training data set D. And the output would be a shallow neural network that learns the decision tree boundaries of the decision tree. Now, this shallow neural network needs to satisfy a few properties. Firstly, it can only use approximate activation functions, polynomial approximate activation functions. So, and we'll describe what those functions are in a minute. And the second restriction is that it cannot be computationally too deep. So that naturally limits the number of layers that you can use in these neural networks. So first we start with a random training data set or a synthetic training data set that sort of distributionally is similar to your original data set D, right? And then we perform a decision tree inference, and this is done in the plain, like on the cloud in the plain text space on the D prime, and obtain all the corresponding outputs of running D prime on the original model DT. Now you take these outputs y hat and D prime and inputs D prime, and now you train a shallow neural network on top of that, right? And then you obtain this neural network N that can act as a proxy for your original original decision tree model DT. Okay. So this is the overall approach on how we do this knowledge distillation. So the table on the right shows you the different types of polynomial activation functions we use. These are different polynomial approximations of your popular machine learning activation functions such as sigmoid, ReLU, Swish, and so on. And then we sort of build a architectural search around these activation functions by playing around with different configurations of a shallow neural network or a candidate student network. So the general skeletal structure of these neural networks is an input layer, one or two hidden layers, and an output layer with C nodes if it's a C-way classification problem, if there are C types of target variables. So the search configurations for one hidden layer include 8 to 64 nodes, hidden nodes, and for C2 it's two hidden layers with different varying number of nodes as shown here. And we perform an architectural search by trying out different nodes here and basically picking the best possible best architecture suited for that particular problem. Okay, so this slide shows you the impact of performing an architectural search on the performance of the model obtained. So clearly we can see that the ensemble performs best because it's non-FHE or non-private score. So that'll be the best. But the second best is the architectural score, which is significantly better than any of the individual configurations. So if I choose any fixed configuration, it's significantly worse than if you perform an architectural search on on the entire search space. Okay. On the second line, the second plot here shows that on the data sets that we have looked at, approx sigmoid performs the best over all the models. It's the two layer. So for rest of the experiments, we basically just we restrict ourselves to the architectural search involving only approx sigmoids. So we validated the approach with several experiments. We conducted experiments on 4 different types of data sets. Most of them are UCI repositories, and the all-state data set here is a Kaggle data set. So the experimental setup was as follows. You train an AdaBoost based ensemble model with 100 estimators, and the green line basically shows the performance of that target ensemble model on each of these data sets. Okay, and then there are 2 bars here, the blue bar and the orange bar, which shows performance of 2 different types of models. So the blue bar represents the performance of a model trained by our approach, and the orange bar is trained by a simple neural network of similar structure, but with only whatever training data is available. There is no synthetic data used here, no distillation involved. So you can see, and we vary for each data set we vary the amount of training data set that we have stored from 10, 1 and 0.1%. So it's a decreasing geometric progression with a factor of 10%, 1% and 0.1%. And then we basically run, perform inference on these models and perform and plot the results. You can see that the blue line is more or less stable as the data size available amount of data set decreases, whereas the orange model, which is just using the original training data set, falls very sharply. So this basically shows that distillation has a clear impact, and all these inferences are performed on encrypted data. So to conclude, we have demonstrated empirically that knowledge distillation can be quite powerful in performing FHE-based inference on complex nonlinear models, and it is our hope that this will spur more research on developing efficient surrogate-based approaches for FHE inference. Thank you. Any questions?